Last time I said I'm even going to try to do it in a simpler way. And today I'm even going to show you in a even simpler, like simpler way, the simplest possible way that we can think about it, all right? And as part of that, I'm going to be introducing to you something called the instrumentation amplifier. Now that right away should raise like a bit of an antenna. What does that mean, right? This class is called Biomedical Instrumentation. You're saying that there is something called an instrumentation amplifier? Correct. And as you might imagine, it's very useful in biomedical instrumentation. In fact, it may be the single most useful chip that you could use. And it's also the simplest to use, all right? And so when the instrumentation amplifier that you have is a chip, right? As you now know, we'll have some pins on it. Two of those pins are the input pins. And one of those pins is the output pin, right? It doesn't have to be in this configuration. As you now know, you need to power your chip, right? Some chips require ground and some do not. And the final piece to this, right, and this is why it cannot be possibly any simpler, is you take a single resistor and you connect it between two of the terminals. And I'm just going to call that RG for now. And this is how you build an instrumentation amplifier. And the reason I'm starting here is I want to show you that based on what you understand so far, it couldn't be any simpler. What do I mean it couldn't be any simpler? You have to have inputs, right? With any op amp. You have to have an op amp. You have to have an output, right? So that is as simple as it gets. And you have to power it. So these are givens. So the simplest possible thing, right, that you could sort of modify or build with this is to add a single resistor. And as we're going to be discussing, this design here is unbelievably powerful. It's so powerful, for example, that by itself, you can collect an EKG, a biopotential. By itself, right, you can collect a brain potential. By itself, you can do so many things. It's that powerful. It's so essential in biomedical instrumentation. Now, we haven't talked about biopotentials yet and other things. So I'm doing things a little bit different, right, where I'm giving you the tools. And then once you have this tool, you're going to be amazed at how much you can do so easily. All right. So we need to build up a little bit to the story. And so I'm going to introduce to you another op-amp circuit called a difference amplifier. And if the follower was, I forget, was A, and then we did inverting and non-inverting, this would be number D. So here's the circuit for a difference amplifier. Yes?
So that op-amp, right, is that the one we just use in our boxes, like it's the exact same one, or is it like a different type?
Great question. So the question is, up to now you've been using op amps, right? You've been taking out chips that are called, regular op amps. This is different. This one is an instrumentation op amp, and we'll describe what it is. So no, it is a slightly different, even though it looks on the outside exactly the same, a rectangle with 4 pins, it is different, but you do have it as well.
But how do you tell which one is the instrumentation op amp? Is it the one with the little stick?
So there should be some sort of label on it, some number, and so that's how you would know. So it could be 7300, and you're saying, oh, that's that's a regular op amp. It's a it's a 9000 series. You'll find out that that's an instrumentation amplifier. Okay. But before that, I want to show you a difference amplifier. And here we're going to start with, I'm happy you brought it up, a regular op amp. And this is how we're going to connect it. We're going to have 2 inputs, and now I'm going to call them V1 and V2. And that right away is different because we've always had one input. One output, I'm going to call it V out. And then for this other input, okay. Two inputs, one output. These resistors can be called R sub B, doesn't matter, R sub A, R sub C, and R sub D. This is a difference amplifier. It looks a little bit like an inverting with a non-inverting. It seems like we've combined a couple things here, right? We're going to figure out what this does. Now, I've talked before about derivations that I will give you and that you will never do again, unless maybe one day you're teaching this class to someone, right? The point of this derivation is not that it's not something you're supposed to memorize, right? It's not, the point of this is I just want you to follow through the logic, because if you follow through the logic, which is not hard, when we get to instrumentation amplifier, it will make sense to you, right? So that's why we're really doing, that's really where I want you to follow along. One of the things I'm going to do right now to simplify it is I'm going to set RC equal to RA, and therefore RD will equal R sub B. Now, what does that mean? Well, I'm picking these resistors, right? I'm picking these resistors. So I could have picked 1 ohm, 10 ohm, 100 ohm, 200 ohm. I'm going to be picking them specifically so that whatever I pick here is going to be the same value as here. So if I pick 1 ohm here, I will pick 1 ohm here. If I pick 10 ohm here, I will pick 10 ohm here. Now, I'm not telling you exactly what these values are as we go through it. I'm just telling you that they are the same. So we can say that this here is now the same as, just write like this, RA, right? And this one here, for our purposes, is RB. Okay. Now, as we've done before, you're faced with a new circuit that you have not seen before, right? But I've told you, take a breath. They're never complicated because there's only two rules that you need to apply, right? The two rules of op-amp, right? So, and then I said after you apply those rules, the op-amp is gone, right? So even though it seems like there's a lot going here, let's just do it. Let's do the two rules of op-amp. I'll do them in green. And I'm just going to draw them out, right? The first rule of op-amp is that the current flowing in to the terminals of the op-amp is 0, right? That's the first rule of op-amp. And maybe you don't need to draw it. Maybe in your mind, I got it, right? I'm just drawing it. Done, halfway there. The second rule of op-amp says that when you have negative feedback, and there is negative feedback here, there are other things going on, but you can draw your finger from the output to the negative, that V plus is equal to V minus. That's the second rule of op-amp. Let's write that here. V plus is equal to V minus. Second rule of op-amp. And just like that, we don't need to think about the op-amp anymore. What could be simpler? I mean, one rule could be simpler. That's two. What does it mean we don't need to think about it anymore? It means that for the rest of the analysis, you can assume that it's not there, right? It's perfect. You can erase it and do the analysis. All right. As before, now we've exhausted our rules of op-amp. So we now need to sort of figure out what's going on here. And again, here, there's no necessarily fixed rule other than that we're going to be using, right, an equation. What equation? Ohm's law, right? Why not? Because it will get us to where we need to go. All right. So here, and again, the reason I'm looking at my notes here is not because you just couldn't do it randomly, because we're trying to do in the least number of steps. Okay, so that's why I'm consulting my notes. I want to start by applying Ohm's law here. So, okay, it seems a bit confusing, right? I want to know what V plus is in terms of V2, R, and RB. So what is that? Have we seen that before? Right? Forget everything else. Forget everything else. If I just drawn this on the board, what are we looking at here? It's just a voltage divider. But you can say, but what about this part of it? This part of it is gone. We removed this part of it. So interestingly enough, it's just a voltage divider. And with voltage divider, you could do Ohm's law and then Ohm's law and solve it, but I also said that's a good one just to memorize, right? And so what we would say is, we would say that V plus is equal to V2 times R sub B over R sub B plus R sub A, right? So that is the voltage here, right? V plus, and we have V minus. All right. The next thing I want to do is I want to write Ohm's law twice. I'm going to do it for this current and for this current. All right, so these are the two currents. I'm going to call this, you can call it I. Now, if you remember from our discussions before, this is the same I. I could write IRB and IRA, but it's the same current. It has to be, right? Just from our intuition, if this is 1 amp, this has to be 1 amp because of this rule of op amp, right? But I'm still going to write Ohm's law here, and then I'm going to write Ohm's law here, all right? And so what I'm going to get is that, first in this case, V out minus V minus, the voltage here, divided by R sub B, that's equal to I, all right? But also equal to I, so I'm just going to put it in pink. Also equal to I is going to be V minus V1 over R sub A. So I've just done Ohm's law twice, and I know that this current is equal to this current, so I saved myself a step and I just wrote it like this. So far, so good? Okay. Now a little bit of simplification of this term here. And so what we're going to do is I'm going to say that, do that here. I'm going to say that V out minus V minus is equal to, I'm going to say R sub B over R sub A times V minus R sub B over R sub A times V1. Hopefully that's fine. Yep. And then I'm going to say V out is equal to, I'm just going to move this V minus over and combine it with that. So I'm going to say 1 plus R sub B over R sub A times V minus R sub B over R sub A times V1. Great. And now what I'm going to do is I'm going to substitute something in here for this V minus. I guess I should have laid out the problem, right? What I would like is I want V out as a function of V1 and V1 and V2. I mean, that's sort of the goal, right? Because I have an output and I have two inputs. So that's always generally been the goal. Though in this case, I have two inputs. So this is what I'm aiming for, right? And I have not motivated this. I'm just saying that's what I would like to do. I want to know what this output is in terms of these inputs. Okay. So here I got output in terms of V1, but I have this V minus hanging here. So I want to get rid of this V minus. I've used this. I can get rid of the V minus by using this here, right? I want to take this, right, and I want to use it. And the way I can do that is by relying on this equation here, which has been sitting here for us. I know that V plus is equal to this, but V minus is equal to V plus. And so V minus is equal to this. So now I'm going to plug that in there. V out times 1 plus R sub B over R sub A times V2 times R sub B over R sub B plus R sub A minus R sub B over R sub A times V1. I now have my V out is equal. I now have my output in terms of the things that I wanted, which is these inputs here. Turns out this simplifies quite a bit because this here is the same as, this is R sub A over R sub A. So it's the same as R sub A plus R sub B over R sub A, right? This is R sub A plus R sub B over R sub A. And you can see how you get the R sub B plus R sub A here, right? These sort of cancel out. And so what we're going to get is R sub B over R sub A times V2 minus R sub B over R sub A times V1. So therefore, V out. And so therefore, we get this final equation, which is that we have R sub B over R sub A times V2 minus V1. And this is the equation, right, for a difference amplifier. Now you'll notice a lot of times when these circuits have a name, it's a good name, right? It gives you the name of what it does. It's an inverting amplifier. It's a non-inverting amplifier. This is a difference amplifier. It does a mathematical operation for you. It takes the difference between two numbers. So if you wanted to make a circuit that took the difference between 4 and 3, or 2.1 and 1.7, now you know how to make that circuit. It will also put, as we talked about before, a gain. Now, you could set this gain to 1 by having these values be equal, right? So if this is 1 ohm and this is 1 ohm, this circuit just produces a difference. Now, I think that's a little bit interesting. It's always interesting to me when you have circuits, right, that are doing these mathematical operations, right? It means that you can make computers that do math and law, right? There's something there about it. But anyways, from the initial perspective, all I want you to understand now is that this output is simply going to be equal to the difference between the inputs times some sort of multiple. And that's why it's called the difference amplifier. It means that if you have any 2 points on a circuit or on the body, and you want to know what the difference between those points are, you would use this circuit to measure the difference between 2 points, right? Which is subtly different than measuring 1 point relative to some reference that's built into your circuit, right? And why this is so useful will become apparent as we start using this in examples, all right? So far, I'm just trying to follow the story, okay? All right. Now, you'll notice that I defined RB and RA, but in so doing, I also defined RC and RD, right? Because whatever these are will also determine these. And if this is not the case, you're not going to get this derivation. It won't come out this elegant, right? Something else will come out. The only reason this came out so simple is because I set these parameters up. I chose it that way. All right. We're now halfway to operational amplifier. Halfway. A few more thoughts to cover.